In this image, a view of electronicity in the ionosphere at the 350 kilometer level. These simulations portray the northern hemisphere in winter with the sun at the top and the Earth rotating below. The color scale on the right shows logarithmic electron density. On the left is a bar showing geomagnetic activity, which is the direction magnitude of the interplanetary magnetic field, or IMF. Ionospheric plasma consisting of electrons and ions is created by solar ultraviolet light on the day side and rotates with the Earth into the night side, producing an ionization tail. Auroral precipitation of energetic particles forms an oval centered around the geomagnetic pole. This oval provides the major source of nighttime ionization associated with solar winter. The vectors indicate direction and magnitude of charge, motion, dynamic electron model. Dynamics present, density contours become much more complex, often resembling thermal convection patterns.
The Tsunami Wave project team developed a numerical model that solves shallow water equations on a grid of about 1 by 1 kilometer, taking into account bathymetry, bottom friction, and Coriolis force for calculations of the wave propagation in Cook Inlet. The interactive grids used for run-up computations are much finer, up to 20 by 20 meters. Simulating low tide conditions similar to the 1883 event, the tsunami wave propagates outward from the Burr Point landslide on the island's northern shore. The propagation is faster in the deep water to the northeast and slower on the shallow shelf to the south of the island. The wave's amplitude generally decreases with the distance from the islands, but strongly increases in the narrow bays and shallow Cook Inlet coastlines.
Now we will enlarge a region of the satellite images near the terminus of the glacier and repeat the animation sequences. In the first high-resolution sequence, the enlarged images are displayed at equal time intervals. The terminus of the glacier, Vitus Lake, and Tagland can be easily identified. This region of the glacier shows relatively little motion until the arrival of the surge front, which appears in the right center in mid-September. In subsequent images, the flow of the glacier over the surface features is clearly visible. In the time-corrected high-resolution animation, the surge front enters the upper right about day 100 and moves to the terminus of the glacier by day 135. The display times have again been adjusted to produce a time-corrected animation, and the 220-day gap between images in the second half of the animation was filled using a morph based on the actual ice field movement. The closely spaced linear features paralleling the direction of flow near the end of the sequence are crevasses that appeared after the passage of the surge front. While I covered up the Miller's 3 and the larval drift emerge current, In this animation, pollock larvae populations are modeled in the northern Gulf of Alaska using a regional ocean circulation model coupled with a biological model of egg and larval growth. Color contours indicate ocean salinity and black crosses show the positions of pollock larvae. This research may help scientists better understand the reasons for yearly variations in pollock populations. polar quantity in the ionosphere at the 350 kilometer level. These simulations portray the northern hemisphere in winter with the sun at the top and the Earth rotating below. The color scale on the right shows logarithmic electron density. On the left is a bar showing geomagnetic activity and axes which show the direction and magnitude of the interplanetary magnetic field, or IMF. Ionospheric plasma consisting of electrons and ions is created by solar ultraviolet dioxide. Oval provides the mission associated with the aurora during polar winter. The vectors indicate the direction and magnitude of charged particle motion in the dynamic electromagnetic model. With dynamics present, the density contours become much more complex, often resembling thermal convection patterns. Ion drift follows the equipotential contours of the electric field of magnetospheric origin. This electric field is highly variable and depends on the instantaneous orientation of the Y and Z components of the IMF combined with the Earth's magnetosphere. In the next animation, the Y component of the IMF is instantaneously reversed every hour, resulting in equipotential contours similar to those shown. This change alters the dynamics of the system and results in changes to the electric field and the corresponding ionospheric convection patterns. The IMF field reversals are readily observed in the reversals of the charged particle vectors. Plasma flow away from the day side changes its direction under the influence of the Y component reversals. The flow is partially destroyed and islands of high ionization density are created. When the convective pattern centered around the geomagnetic pole is on the day side, the effects are much more prominent compared to night side occurrences. Now the effect of field reversals in the Z direction will be explored. The positive Z-axis is aligned with the north polar axis perpendicular to the plane of the screen. In this animation, the Z component of the IMF is reversed instantaneously every hour. This leads to much more dramatic changes in the corresponding electric field pattern and the ion motion. The field reversals are again immediately apparent from the reversals in the charged particle vectors. The positive orientation of the Z component suppresses convective motion, while the negative orientation corresponds to the most intense convection patterns. These instantaneous changes in the dynamic model create a highly variable plasma density in the center of the convective pattern inside the auroral oval. This is the so-called polar cap. This graph shows actual IMF measurements for a powerful magnetic storm which occurred near midnight on March 20th of 1990. It is evident from these data that several reversals of both the Y and Z IMF components took place during the period. The final animation uses the observed variations of the IMF to simulate a 48-hour period. The direction and magnitude of the observed IMF are shown on the axes in the lower left. The first day has moderately disturbed geomagnetic conditions. A magnetic storm begins about 20 hours UTC and continues throughout the second day. The storm generated extremely fast convection drifts with velocities exceeding 2 kilometers per second. Joule heating drastically increased the temperatures and accelerated the chemical processes, resulting in general depletion of the ionization density throughout the entire polar region. These model predictions for space weather show good agreement with actual ionospheric data and may someday allow scientists to accurately forecast ionospheric conditions.
Volcanoes and the sea, powerful forces in nature, two of the most unpredictable and unstable. Transitions from quiet and peaceful to eruption and storm are fast and imminent. leaving almost no time for preparation, let alone escape. Their union causes another phenomenon which challenges its parents in the scale of destructive force, the tsunami wave. All of these are natural occurrences in Alaska. The divide of Pacific and American tectonic plates is marked by a chain of active volcanoes that cross Alaska. Several volcanoes are situated in the vicinity of the densely populated areas around Cook Inlet, a 300-kilometer-long estuary in southern Alaska. The danger of eruption is multiple, not only filling the air with plumes of ash and dust and endangering the intense air traffic in the area, but creating havoc in surrounding bodies of water. One of these volcanoes, Mount St. Augustine, is a small island situated near the west shore of the lower Cook Inlet. Its proximity to the sea makes it a potential source of catastrophic tsunami waves. The volcano was discovered on May 26, 1778, St. Augustine Day, by Captain James Cook during his third Pacific voyage. The diameter of the uninhabited circular-shaped island is about 12 kilometers, and a single volcanic cone rises from its center to 1,250 meters. Mount St. Augustine is a very young volcano formed in post-glacial times. The volcano consists of a central dome complex, dome remnants, and an apron of volcaniclastic deposits. In the past 200 years, St. Augustine has had 6 major dome-building eruptions. Based on historic records, each of these eruptions greatly modified the volcano's appearance. When we compare this volcano sketch made before the historic eruption of 1883 to this island photograph taken in the early 1900s, we see that the eruption completely destroyed one side of the volcano's dome. Debris avalanche covered a 25-square-kilometer area and extended the Burr Point pre-eruption coastline at the island's north side by 2 kilometers. The pre-avalanche shoreline and remnants of debris avalanche are noticeable on this recent photograph. The placement of those deposits into the sea created a tsunami event recorded 85 kilometers across the inlet at the village of English Bay. A series of up to 9-meter-high tsunami waves reached far inland and devastated the village pier and flooded the houses. Fortunately, it was low tide. Otherwise, as a witness states, all of the people of the settlement would have been lost. This simple animation represents a mechanism of tsunami generation by a landslide. The entrance of debris avalanche into the sea results in a displacement of water. The fast energy and momentum transfer from the avalanche creates a tsunami wave, propagating outward from the source for hundreds, even thousands of kilometers. The Tsunami Wave Project team developed a numerical model that solves shallow water equations on a grid of about 1 by 1 kilometer, taking into account bathymetry, bottom friction, and Coriolis force for calculations of the wave propagation in Cook Inlet. The interactive grids used for run-up computations are much finer, up to 20 by 20 meters. Simulating low tide conditions similar to the 1883 event, the tsunami wave propagates outward from the Burr Point landslide on the island's northern shore. The propagation is faster in the deep water to the northeast and slower on the shallow shelf to the south of the island. The wave's amplitude generally decreases with the distance from the islands, but strongly increases in the narrow bays and shallow Cook Inlet coastlines. This alternate view from above allows a better understanding of the interference pattern generated by the interaction of reflected waves. It can be seen that the maximum wave amplitudes occur on peninsula shorelines. English Bay's location on a peninsula, combined with the shoaling coastline, makes it especially vulnerable for tsunami waves. In this simulation, it took the wave 53 minutes to reach the village location on the eastern shore of the inlet. The wave amplitude during run-up is doubled, reaching 3 meters at low tide, which confirms the historic observations. Calculations performed for high tide conditions give the value of 7.4 meters for the wave amplitude at English Bay. This project, funded by the Alaska Sea Grant Program, is a collaborative effort of the Institute of Marine Science, the Geophysical Institute, and the Arctic Region Supercomputing Center, all at the University of Alaska Fairbanks. Because of the present oversteepened summit configuration, the Mount St. Augustine volcano may collapse again, resulting in a tsunami with a destructive wave run-up at Lower Cook Inlet coastal communities. To help provide an effective warning system, the existing tsunami model can be applied to any coastal region threatened by a volcano-generated tsunami.
The Bering Glacier southeast of the stellar and is the largest glacier in North America. Normally, this massive river of ice moves no more than a few inches per day, but in early 1993, the Bering Glacier began a remarkable surge, moving as much as 100 feet in a single day. Using data from the European remote sensing satellite ERS-1, radar images of the Bering Glacier were recorded from November of 1992 through June of 1994. A total of 16 satellite images were processed for the region of the glacier outlined by the box. Supercomputers were used to correct and align the images with known geographic features. This process, called terrain correction, allows the sequential images to be viewed like a time-lapse movie. In the first animation, each satellite image is displayed for the same period of time. Note, however, that the actual times between the images vary from 5 to 220 days. Top-to-bottom motion is clearly visible in the main body of the glacier. A surge front, visible in the center, moves rapidly to the south, reaching Vitus Lake by mid-September. By October, icebergs from the leading edge of the glacier have completely filled Vitus Lake. In this sequence, image interpolation and morphing techniques were applied to produce a time-corrected animation of the ice movement. This was done by varying the display times of the images to correspond to the actual time differences and then interpolating between successive images, resulting in a much more accurate display of the ice motion. Most of the images are separated by intervals ranging from 5 to 22 days. On day 170, there is a large gap of 220 days between images. A morphing operation based on actual ice field motion was constructed at this point and continues through day 390. During this time, the glacier advances into Vitus Lake and covers nearly all of the surface of Tagland. Now we will enlarge a region of the satellite images near the terminus of the glacier and repeat the animation sequences. In the first high-resolution sequence, the enlarged images are displayed at equal time intervals. The terminus of the glacier, Vitus Lake, and Tagland can be easily identified. This region of the glacier shows relatively little motion until the arrival of the surge front, which appears in the right center in mid-September. In subsequent images, the flow of the glacier over the surface features is clearly visible. In the time-corrected high-resolution animation, the surge front enters the upper right about day 100 and moves to the terminus of the glacier by day 135. The display times have again been adjusted to produce a time-corrected animation, and the 220-day gap between images in the second half of the animation was filled using a morph based on the actual ice field movement. The closely spaced linear features paralleling the direction of flow near the end of the sequence are crevasses that appeared after the passage of the surge front.